What if we could solve our planet's entire energy crisis by building our very own star, right here on Earth? It sounds like something straight out of science fiction, right? But believe it or not, it's one of the most incredible scientific projects humanity has ever attempted. So let's dive into this quest for fusion energy. All right, here's our game plan. We're going to start with why we're doing this in the first place, then get into the nitty-gritty of how stars work. After that, we'll tackle the mind-bending question of how you bottle a sun, look at the massive global projects making it happen right now, get real about the huge challenges we still face, and finally, ask the big question. Is this the dawn of a new age for energy? So, first things first, why are we going to all this trouble? Well, the motivation behind it is probably one of the biggest issues facing all of us today. I mean, think about it. Our world needs more and more energy every single year. But we have to find a way to get that power without wrecking the planet in the process. We're not just looking for a quick fix. We need a real, long-term solution that can power our world for generations. And that leads us to this absolutely breathtaking idea that scientists are chasing. It's the idea of copying the very process that powers the sun and every single star you see in the night sky. Now, you've probably heard of nuclear fission. That's where we split heavy atoms apart. This is the exact opposite. Nuclear fusion is all about taking really light atoms, like hydrogen, and squeezing them together. When they fuse, a tiny, tiny bit of their mass vanishes and gets converted into a huge amount of energy. It's literally the most powerful engine in the entire universe. But there's a catch. To get these atoms to actually fuse, you need some seriously extreme conditions. We are talking about temperatures around 150 million degrees Celsius. Just to put that into perspective for you, that is 10 times hotter than the core of our own sun. Unbelievable, right? At those kinds of insane temperatures, you don't have a solid, liquid, or even a gas anymore. Matter becomes something else entirely: plasma. You can think of it as a superheated, electrically charged soup where atoms are torn apart into nuclei and electrons. And this is the stuff we have to create and somehow, miraculously, control. Which, of course, brings us to maybe the biggest engineering puzzle imaginable. If your fuel is 10 times hotter than the sun, what in the world do you keep it in? You can't just put it in a box. Any material on Earth that touched this plasma would instantly be vaporized. Poof, gone. So the container can't be made of matter. The solution has to be invisible. It has to be a force. And that force is magnetism. The leading design for this magnetic bottle is a machine called a tokamak. It's a fun name, right? It actually comes from a Russian acronym that translates to toroidal chamber with magnetic coils. Ever since it was designed back in the 60s, it's become our best shot at taming a star. So inside one of these tokamaks, you have these incredibly powerful magnets that create an invisible cage shaped like a donut. This magnetic field holds that superheated plasma, squeezing it and keeping it from ever touching the reactor walls. It just floats there, in the middle, getting hotter and hotter. The whole process basically breaks down into 4 steps. First, you inject a tiny bit of hydrogen fuel. Then, you heat it up like crazy until it becomes a plasma. Step 3, you hit it with those powerful magnetic fields to trap it. And finally, you squeeze it until the atoms fuse and release all that incredible energy. Okay, so this isn't just some theory on a chalkboard. This is really happening. We are building these things right now, thanks to one of the largest and most ambitious international projects in the history of science. You know, the road to get here has been a long one. Serious research kicked off way back in the 40s. The tokamak design really took over in the 60s. And then, in 1985, the idea for a giant international project called ITER was born. We've seen amazing progress since then, and the next huge milestone is right around the corner. And when I say this effort is global, I mean it. The ITER project, which is being built as we speak in France, is a massive collaboration. We've got 7 members, but they represent 35 different countries. It's basically Team Earth coming together to make this happen. And we are seeing some truly jaw-dropping breakthroughs. Just recently, China's artificial sun, a tokamak called EAST, set a new world record. It managed to sustain a high-temperature plasma reaction for over 1,066 seconds. That's more than 17 minutes. It might not sound like a lot, but in the world of fusion, that is a gigantic leap forward. It shows us that keeping this reaction stable for a long time is actually possible. Now, as exciting as all of this is, we've got to keep our feet on the ground. There are still some enormous, truly difficult hurdles to overcome before fusion energy is powering our homes? There are really four big ones. First, and this is the holy grail, is achieving net energy gain. That just means getting more energy out of the reaction than you put in to start it. Second, that plasma is wild and unstable. Just keeping it contained is a constant fight. Third, the materials used to build the reactor have to survive being bombarded with intense radiation for years. And finally, there's the fuel. One part of it is abundant, but the other, tritium, is super rare and has to be created inside the reactor as it runs. But even with all those challenges, the final prize is just so huge, so world-changing, that it keeps driving this incredible global quest forward. And here's why. The promise of fusion is nothing short of a practically limitless and totally clean source of energy for all of humanity. Its main fuel, an isotope of hydrogen called deuterium, can be filtered right out of ordinary seawater. That means the fuel supply will basically never, ever run out. And on top of being limitless, the payoff is just wow. Fusion power creates zero greenhouse gases. It's also inherently safe. There's no risk of a meltdown. If something goes wrong and the magnetic field fails, the reaction just stops. And the radioactive waste it produces is so much less dangerous and doesn't last nearly as long as the waste from our current nuclear plants. So the road ahead is long, and the challenges are, frankly, immense. But for the very first time in our history, the dream of harnessing the power of a star is moving out of physics textbooks and into the real world of engineering. The answer to this question could truly define the entire future of our civilization. If this explainer sparked your curiosity, make sure you like and subscribe so you don't miss what we break down next.